Hello everybody, in this video I'm going to go over section 4.7 antiderivatives. So the word anti means opposite, and that is what we're going to do. We're going to look for functions that when you compute the derivative of these functions, you get the function that we had to begin with. And obviously we're going to go over the definition, formulas, properties, and then we'll do some examples, okay? Now, the actual definition, let's say I give you f of x equal to x, okay? So now I want a function whose derivative is x. Meaning, say for example, I had a function to begin with. I applied the derivative, right? I use the formulas and it takes me to x. So what we're doing now is, what is that function, right? That when I took its derivative, it took me to x. And that is what we're going to call the antiderivative. Now, hopefully, you were thinking about it, right? And you came up with x squared. Well, if I compute the derivative of x squared, it does take me to 2x, right? Well, that's not enough. I need x. So I divide by 2, that'll give me x, so I have to divide x squared by 2. So then we're going to say that x squared divided by 2 is the antiderivative of x, right? So I can say x squared divided by 2. If I take the antiderivative, it takes me to x squared divided by 2. If I take the derivative of x squared divided by 2, it takes me to x. Beautiful. But now, if I take the derivative of x squared divided by 2 plus 5, that is also equal to x because the derivative of a constant is 0. If I take the derivative of x squared divided by 2 plus pi, that is also equal to x because the derivative of a constant is equal to 0. So what I'm saying is that if you think about it, we're going to have a family of antiderivatives. So I'm going to write that down. So what I'm saying is that x squared divided by 2 plus any constant c is the family of antiderivatives of x, okay? Where c is constant. And you don't get to choose that constant, okay? So from now on, if I ask you to find the antiderivative of a function, you're going to tell me the antiderivative and you will add a constant plus c. Perfect. Now let me give you the actual definition. So definition, so we're going to say that capital F of x is an antiderivative of little f of x if when I take the derivative of capital F, it takes me to little f of x, okay? Perfect. Note, the most general antiderivative of f of x is, well, capital F plus some constant, okay? And now, to make things easier, I'll give you some notation. So notation, and this notation is from section 5.2, okay? So when we go over section 5.2, it'll become clear why this is the notation. For now, we're just going to use it just to make things easier, okay? I'm going to use this symbol. This is an elongated S from Old German, okay? And I'm going to put my function here, and I'm going to write dx, okay? So this dx means that I'm finding the antiderivative of my function f of x with respect to x. And I will say that this is equal to capital F of x plus a constant if and only if when I take the derivative of capital F, I get the little f in between the two symbols, okay? Perfect. So now let's go over the formulas, okay? Now let's go over the formulas one more time. This is my notation from section 5.2. So now the first one is I'm looking for the antiderivative of x to the n, okay? And I'm saying here, hey, look, the antiderivative of x to the n is x to the n plus 1 divided by n plus 1. And as usual, at a constant, okay? Now, there are two ways of thinking about this, and there are like two ways like why it makes so much sense, okay? If you think about it, we're saying that the antiderivative is the opposite, right? Well, when I compute the derivative, I multiply by the exponent, and I subtract 1. Now we're doing the opposite. Now we add 1 to the exponent and divide by the new exponent. Okay, you can also prove this super easily. Let's just prove it, right? You can just prove it. So we know that if I compute the derivative of xm plus 1 divided by m plus 1 plus some constant, so, or c constant, we get that I'm going to bring the exponent to the front, so I get m plus 1 x, m plus 1, I subtract 1 because I'm computing the derivative, and divide by what I had in the denominator, so n plus 1, and then the derivative of a constant is equal to 0. So I get that this goes away, 1 minus 1 is equal to 0, so I get x to the n. So I'll give you a second so you can do these examples on your own, and then we'll discuss it. Well, notice that the formula is for a power function, okay? So the exponent will be my n. I add 1 to the exponent, I subtract by the new exponent, and I have to add the constant, okay? So if we go to the first example, we have x to the 6, so 6 is my n. So I will add 1 to the exponent, so 6 plus 1, you get 7. Divide by the new exponent, you get 7. And then add a constant. You always have to add the constant, okay? Perfect. Now I go to the second one, when then I know that I have to rewrite this so that it looks like x to an exponent. So I have x to the 1/2 dx. So I'm just rewriting it. Now I'm going to take the antiderivative. So I get x to the 1/2 plus 1 divided by 1/2 plus 1 plus a constant. And then I finally get that this is just x to the 3/2 divided by 3/2 plus the constant, right? Because 1/2 plus 1 is equal to 3/2. Yeah, I did it right. That's it. And then I go here, I have x to the negative 2, add 1 to the exponent, divide by the new exponent. So I have that this is x minus 2 plus 1 divided by negative 2 plus 1 plus a constant. And this is equal to x to the negative 1 over negative 1 plus a constant. Super easy, right? Super easy. So now we can do the next one. Now we have that, again, I have the antiderivative of 1 over x dx. So the very first step is to rewrite it. I have x to the negative 1 dx. And this is equal to, well, we use the same formula, right? Add 1 to the exponent and divide by the new exponent. So you get x to the negative 1 plus 1 divided by negative 1 plus 1 plus it. What? What happened? Was that dramatic enough? Right? You cannot do this. If you do this, you're dividing by 0. You can't do this. So you have to go back and think, can you think of a function whose derivative is 1 over x? And this is rule number 2. Now the antiderivative of 1 over x dx, it's equal to the natural log of x plus a constant because, well, the derivative with respect to x of the natural log of x, it's equal to 1 over x, okay? And I'm using the absolute value because you know that the domain of the natural log is any real number larger than 0, okay? Now we're going to derive the rest of the formulas by thinking of the definition of the antiderivative. So, can you think of a function whose derivative is e to the x? Yes, e to the x plus a constant. Can you think of a function whose derivative is cosine of x? Yes, sine of x plus a constant. Can you think of a function whose derivative is sine? Yes, negative cosine of x, right? Think about it for a second. Think of it for a second. If I take the derivative of cosine, that will take me to negative sine. So I need that negative in front of cosine so that it takes me back to sine, okay? Can you think of a function whose derivative is secant squared? Hopefully, you're saying tangent of x plus a constant. and a function whose derivative is 1 over 1 plus x squared? Yes, indeed. This is arctangent of x plus a constant. Okay? So now, some properties of antiderivatives. Well, same properties that derivatives have. So for example, let's say the first one is, if I have the antiderivative of a sum or a difference, it's equal to, well, the sum or difference of the antiderivatives. And this is super important because that tells me now that I can take I can find the antiderivative of a sum, okay? 2, if I have the antiderivative of a constant times a function, then I can just take the constant out, just like we did for derivatives, okay? Now, obviously, I'm not going to go over other properties, but if you think about it, everything that works for derivatives will work for antiderivatives. So I'm not going to give you anything about product. I'm not going to give you anything about chain rule because we don't know it yet. We don't have it yet. Actually, you're going to see those things in Calculus 2. So now that we know this, these properties, we can solve some problems, okay? So let's do some examples. The very first one is, I'm looking for the antiderivative of 100. So my question is, can you think of a function whose derivative is 100? Can you think of a function whose derivative is 100? Yes, right? 100x. So then the beauty of antiderivatives is that you can always check your work. You can always check your work. You can always say, okay, I know that the antiderivative of 100 is equal to 100x plus c, because if I take the derivative of 100x, I get 100, and the derivative of a constant is just 0. Okay? Perfect. Now for the second example, as I was saying like 3 seconds ago, we don't have anything for products. Okay? So if I have something like x times x squared plus 3, the very first step is to multiply them together. So now I get that this is actually the antiderivative of x cubed plus 3x dx. And I know that the antiderivative of a sum is the sum of the antiderivatives. So I can go term by term, okay? Let's see. So if I take the antiderivative of x cubed, I have x. Now the exponent is 3, so I have to add 1 and divide by the new exponent. Ready? So 3 plus 1, you get 4 divided by 4. And then I have plus 3x. So I have 3, right? So I know that the antiderivative of a number times a function, I can take the number out and find the antiderivative of here, right? I take the 3 out, so 3, and then I multiply by the antiderivative of x, which is add 1 to the exponent, so x squared divided by the new exponent. And then you add a constant. So same thing here when it comes to the third example. If I have the antiderivative of x plus 2 divided by x, I don't have anything for quotients, right? So I have to use algebra first, and like we did for example number 2, I will rewrite this as x divided by x plus 2 divided by x dx. Okay, so this is just the antiderivative of 1 plus 2 divided by x dx, and I can go term by term. So if I go term by term, I get that the antiderivative of 1 is just x, because if I take the derivative of x, I get 1. And then I know that my rule, the one where you add 1 to the exponent and divide by the new exponent, it works for everything except for n equals -1, except when I have 1 over x. So I know that this is 2 times the natural log of x, and you have to add a constant, okay? Perfect. We're good? How do we feel about this? Are we good here? So I have now problem number 4. So again, I'll give you a second. Think about it, right? I just have 3e to the x plus the cube root of x plus 1 over 1 plus x squared plus sine of x dx, okay? So if I go term by term, I get that this is, well, 3 times e to the x, because the antiderivative of e to the x is itself. Then here I have to make it look like a power, so I know that this is just x to the 1/3. So if I have 1, so 1/3 plus 1, I get x to the 4/3 divided by 4/3, right? Then I need to find the antiderivative of 1 over 1 plus x squared, which we know is just arc tangent of x, plus the antiderivative of sine, which is negative cosine, so negative cosine of x. And you always need to add the constant, okay? We will take points off if you don't add the constant. And now we do a more interesting example. So remember how I told you a couple of minutes ago that you didn't get to choose the value of c, the constant? Well, that is true if you're looking for the general antiderivative of a function, okay? But if I'm looking for a very specific function, then if I have conditions, I can actually find the value of the constants, okay? So what I'm saying is, say for example here, we want to find a function f whose second derivative is equal to sine of theta plus cosine of theta. Then if I substitute 0 into the function, I get 1. If I substitute 0 into the derivative, I get 4, okay? Now, think about it for a second, right? If I start with my function f, and I take the derivative of my function with respect to theta, that'll take me to f prime. Then if I take the derivative again with respect to theta, that takes me to f double prime. And that is what we have in this example to begin with. We have f double prime, and we're looking for f. So if we want to find f, then what we do is, well, we take the antiderivative. If I take the antiderivative of f double prime, I'll go back to f prime. If I take the antiderivative again, that'll take me to f, okay? And then I use this information to find what the value of the constants are. Okay, so let's do it. So let's say, okay, so for example, what I'm saying is that now I know that f prime is equal to the antiderivative of my f double prime. So I'm going to write it. So I get that f prime of theta, it's equal to the antiderivative of f double prime of theta d theta. But I know what f double prime is. F double prime is equal to sine of theta plus cosine of theta d theta. And since I'm adding two functions, I can find the antiderivative by going term by term. So I get that this is just negative cosine of theta plus sine of theta plus a constant, okay? So if you think about it, now we have that f prime of theta, it's equal to negative cosine of theta plus sine of theta plus c, right? Well, that means that if I substitute 0, I have to get 4, right? If I substitute 0 into my derivative, I have to get 4. And this is the information we're going to use to find the value of c, okay? So now I have that f prime of 0, it's equal to 4. So that tells me that if I substitute 0 into f prime, which is negative cosine of 0 plus sine of 0 plus c, I have to get 4, okay? Well, we know that cosine of 0, it's equal to 1, so this is negative 1 plus 0 plus c, it's equal to 4. So that tells me that, well, c it's equal to 5. So what that means is that my function, like the derivative of my function, so f prime of theta, it's actually equal to negative cosine of theta plus sine of theta, and then you get to replace c with 5, the value of the constant, so plus 5. Okay? Now I'm not done. I'm actually looking for my function f, okay? So then if I want to get to f, I have to do this again. Now I have to find the antiderivative of f prime. So let's do it. So now I know that f of theta, it's equal to the antiderivative of f prime of theta, d theta. Well, f prime of theta, d theta, it's equal to cosine of theta plus sine of theta plus 5. So I'm going to take this with me, and I get that. So now I get that I'm looking for the antiderivative of my f prime with respect to theta. Okay, so now I do it again and I get that the antiderivative of cosine is equal to sine, so I get negative sine of theta minus cosine of theta plus the antiderivative of 5, which is 5 theta, plus a new constant. And notice that I'm using C for this constant, but I'm going to actually call it D so that you know that this is not the same constant. This is some other constant, the constant that came from taking the antiderivative of f prime, okay? Right? And then I go back, and again I see that f of 0 is equal to 1, okay? F of 0 is equal to 1. So f of 0 is equal to 1 tells me that if I substitute 0, if I plug 0 into my function, I have to get 1. So then I get negative sine of 0 minus cosine of 0 plus 5 times 0 plus d, it's equal to 1. And this is the case if only, well, I know that sine of 0 is still equal to 0, so 0 minus 1, well, plus 0 plus d, it's equal to 1. Solve for d, right? So if I solve for d, I get that d is equal to 2, right? So what does that mean then? So that tells me that I wanted to find f, right? And I know that f is given by this expression. I only had to find the value of d, what I did. D is equal to 2. So now I know that the answer to my problem is f of theta, it's equal to negative sine of theta minus cosine of theta plus 5 times theta plus d, but we know that d is equal to 2, so plus 2. And this is the answer to my problem. This is that function f such that the second derivative is equal to sine of theta plus cosine of theta, f of 0 is equal to 1, and f prime of 0 is equal to 4, and you can check your answer. Once again, this is the beauty of antiderivatives. You can always check your answer, okay? So that's it for now. Thank you for watching, and I'll see you next time.